Nothing yet? Okay. Let's leave this up and get rid of this. We're finally going to get around to answering this question. We've been batting around the bush for quite some time, making up margins of error. Although I think it was good to make up the margin of error. I think it was good because it gives us an idea of, okay, I understand how to use it now. Now, you're going to understand how to calculate it. And since you already know how to use it, then you're golden. Then you're golden. Okay, so we know that please, Ben, go ahead.
To clarify, it sounds like what you do is decide how confident you are.
Yes, sir.
And then
First. Yes, okay. You have to know how confident you are first before creating your interval. Can you see, this is me being a little bit negative, can you see how going the other way would be a problem? If you're a bad statistician. You can look over here and go, okay, here's what we're shooting for. And I got this result. I'll just increase my confidence. Yeah. Until it catches what I'm looking for, and then I can say there's no difference. See, that's the problem. You can't do it post-fact, because you have to go in, and there's also something called power and type 1 and type 2 errors, all of which we'll get to in this class. But yeah, you have to decide I think it's called a priori, I believe is the phrase, before you start. So we're going to pick 95% confidence to generate a margin of error. Thank you, Ben. Very good question. Everybody catch that question? Understand, you want to pick it before you start. You want to pick it. There are other things, as Rory said, there are other things besides the 95% confidence at stake here. There's other stuff. There's a secondary curve you don't know about yet. All kinds of stuff floating around. It's all based on that. So yeah, definitely set it up first. Thank you. Great question. All right, p hat's 41.5. We know that n is 270, and we know that q hat, which is the complement of p hat, which would be the percentage of tails in our sample, is the 58.5%. Thank you for doing math for me. I truly appreciate it because I suck. This is the one and only time we'll crunch this by hand. Never again. Then we start using technology. So they say sweet. Yes, that's very sweet. Because this does get a little bit annoying. This does get a little. All right. So the standard error, which is the standard deviation of the sampling distribution. Can we see this on the video? Barely. So the standard error, which is the industry term for the plus or minus, one plus or minus in the sampling distribution, is that kind of goofy calculation, goofy-esque calculation, big radical. And again, if anybody's interested in why this formula works, I encourage you to watch that 3-minute video. I'll walk you through it pretty carefully, and you see all the math behind it. P hat, Q hat, all over n. Our job is to run the numbers. All you gotta do is run the numbers. Let's do it. This is the most math we'll do today. I promise you, most math we'll do today. Root, P hat, 0.415, Q hat, whatever else, all over 270. Our job now is to calculate that and see what it comes out to be. Let's do it over here. I'll slap it up on the board. I apologize, I thought I had the document camera working, but it's not, so we'll go old school. Okay. I'll do the top first, 0.415 times 0.585, that's the top. Now you got to realize there's some unit analysis issues right now. That number doesn't mean anything. It's two percentages multiplied together, so it's like a square percentage. That doesn't make any sense. You divide it by its number, 270, that makes even less sense. So I'm going to take the square root of that, which will knock percentages squared down to just percentage. And hopefully that makes sense. That's what we want it to be. So the square root of the answer. All right, that's almost exactly 3%. Please.
How did you get the answer thing?
Oh, second enter. No, second negative sign. Second negative sign, Allie. Second negative sign pulls back the last answer you calculated.
Okay.
Is that fair?
Yeah.
So our standard error, that's the cleanest that's ever been. Can you see that? Guys, see that 0.0299 right here? I'll slide it up a little bit here. I've never had a margin of error that clean. It's kind of ridiculous, actually. It's so clean. 3%, excuse me, I used the wrong term. It's a standard error, not a margin of error yet. We have to multiply it to make it a margin of error. So the standard error is almost exactly 3%. We'll do squiggles if it makes you feel better. Fair. Rory, ask me that question.
You have to square it.
Why do you have to square root it?
We always have to square it, but that's supposed to be common sense. And I just
Wait, when you say square,
well, like however you got the second part.
oh, the root?
Yeah.
It's a function of the standard.
Oh, my
right.
bad. Yeah.
That's okay. No, it's not, brother. There's nothing commonsensical about that formula. Seriously. Did I tell you the story? I think I didn't tell you guys I didn't have a 243. When I studied the binomial distribution, I was sitting in your chairs where you were in 243. And my prof just simply wrote on the board, here's the average, mu equals NP. Here's the standard deviation, sigma equals root NPQ. And I'm in the back going, why? Where? Why? Because we had already studied the way you calculate a weighted mean and a weighted standard deviation just like we did in 243. You know, this times this, this times this, this times this, add them up. That all made sense. But why all of a sudden is there a clever formula for this particular distribution? And he's like, oh, it just collapses into that. I'm like, how do you collapse into a radical? Like, I'm just a total pain in the ass student. And I love that. I love when you guys ask me the questions because you draw the best. And he's like, I've been teaching it for 30 years and it's the way it is. And I'm like, ooh, the old, you can't go out because I said so answer. Okay, so then I went home and proved it myself. And there's nothing commonsensical about it, Roy. It's 3 pages of calculations to get to that. Which is why, check the video out, I collapsed it into 3 minutes. It's a little bit easier for you. But it's definitely not common sense. Please don't ever think these are necessarily commonsensical formulas, because they're not. They're clever, they're concise, but they're definitely not simple as to why they're there. Thank you for that, friend. Thank you, thank you. Okay, we agreed on 95% confidence, yes? We did, yes, we did. So the margin of error, now I noticed I've been going back and forth between MOE and ME. I apologize. They both mean the same thing. ME is margin of error, MOE is margin of error. I apologize, depending on which one I write, they both mean the same thing. I'll go with MOE, since I was using it over there. Well, that's going to be 2, roughly, times the 3%, right? Why 2? Why 2? That's going to give you 95%. If we just left it at 1, what's the confidence that we've got? Do you remember the number from the slide? That's at 68%. If we take it to 2, we beef it up to 95% because we picked up 95% of that bell curve by the central limit theorem. If we bump it to 3, we pick up a few more percentage points, but 95% is fairly standard, which means our margin of error, I'm out of colors, which one haven't I used yet? Green, we'll use green. Our margin of error now is right sitting around 6%. So Chris, your question from before, which was so damn good, was, wait, this is all fiction, you're making up numbers, 2, 6, 4, 15. I was making up numbers to get the interpretation now. That is the margin of error that would accompany those sample data. So now we've got it. And now that we've got it, can we apply it to our sample statistic and slap it on our number line over here? I think we can. Because now we do it the exact same way we did with those, except this is the actual correct margin of error. Yes, mathematically. Here we go, over to here. Let's get it zoomed in a little bit better.